Good day, class. I hope everyone is doing well when they start watching this video. Today we're going to be talking about specific heat capacity. So started learning about thermal energy. We even learned a little bit how to calculate thermal energy, but now we're going to be talking about specific heat capacity. And today we're really wanting to just understand it as a unit, and then later we'll learn how to calculate it and what it looks like in problems. But for right now, I just want you to learn how to understand what this word is, or words are. So our questions, always to warm up, get our brains thinking. I want you guys to think about what takes longer to warm up, water or oil, and maybe why. Why is that the case for water or oil? So in my experience, water takes longer than oil. If I'm maybe warming up water to make pasta, that takes a lot longer than if I'm warming up some oil to make tajadas or anything else. And so we'll talk about why a little bit later. I guess right now. It takes more energy to raise water's temperature is why. So if we have the same amount of water, same amount of oil, it takes a lot more energy to warm water up. Also, if we go to the beach, what is warmer, the sand or the water, and why? So if you guys have ever gone to the beach, maybe you've noticed that the sand gets really hot on our feet. And if you're anything like me, I would just go running into the water so I can stand and have my feet nice and cold. And so our sand is warmer, or sometimes a lot hotter, and this is because it takes a lot less energy to raise its temperature. So, objectives, we want to understand what specific heat capacity is by the end of today, and then describe how systems and some environments benefit or are harmed by substances having high or low heat capacity. So that's a lot of big words, but we really just want to see how heat capacity can affect the environment around us. So this is a really good video talking about water in the sand versus heat in the sand versus heat in the water, and kind of what it looks like. We will link that as always. But to talk about specific heat capacity, our very scientific definition is that specific heat capacity is the amount of energy it takes to raise 1 kilogram of a substance, of anything, 1 degree Celsius. So we take 1 kilogram of water, 1 kilogram of oil, 1 kilogram of copper, anything, and we measure how much energy we need to put in to make it go up just 1 degree. So I like to think of this a little bit simpler as just the specific heat capacity is the energy it takes to warm something up. A high heat capacity means it's going to take a long time. So water is our best example of something with a high heat capacity. And we can see over here in our table that water has a very high heat capacity, much higher. It's at 4.1, while everything else is not even at 2. Our next closest is oil, which is almost at 2 joules per gram degree Celsius. So water takes much longer. We have to put a lot more energy per kilogram into water as we do for any one of our other examples. The other way means that if you have a low heat capacity, if we have a low heat capacity like lead, it warms up very quickly. So that means we don't have to put much energy in for it to raise a little bit, 1 gram a degree Celsius. So maybe we just have to put it, I think on the stove is what I think of, for maybe even 10 seconds, and it will raise the temperature really quickly. So we have lots of examples. Our table shows silver, copper, iron, lead, but we've also talked about sand and then oil as well. These all warm up very quickly. So this is a good thought experiment that I want you guys to look at. So we're going to watch the video and then answer some of the following questions. So I want you guys to really observe and see what happens. So we have one balloon. We put it above the flame and nothing happens. Doesn't pop, nothing happens. We set it back down. We put the next balloon up against the flame and it bursts. So, some of the questions. What was in the first balloon? Do you guys have any ideas? It looks kind of heavy in it, and then they set it back down, and it kind of sat a little bit different than a normal balloon would. What was in this? Oh, that should say second. What was in the second balloon? Sorry about that. Second balloon. Why did the first balloon not burst, and why did the second balloon burst? So, the first balloon, once you guys have thought about this, some of the explanation behind it is our first balloon is full of water. So we could even see it looks kind of squished inside when you set it back down on the table, I should say. So it's not heating up, and then they lay it back down. And if you guys have ever done a water balloon fight, you notice that our balloons, when they have water, kind of squish like this. So it has water, and it didn't burst because all of the energy from the candle went into the water, and the water took all of that energy and didn't change temperature, didn't burst. But our second balloon was full of air. And so since the air got heated up quicker, it burst the balloon because all of the molecules wanted to get out of the balloon as fast as they could. So that just shows that water's heat capacity is much higher than air's, and so it can absorb the energy from the candle. All right. Now let's talk about how this affects our environment. So we have different ecosystems, different environments that have different terrain, different things, whether it's water, whether it's trees, whether it's sand, and it will affect how that environment looks. So I want you guys to think, what is a desert like? Maybe try to describe it. The words that come to mind for me is dry. I would think really hot or really cold. At night it gets really cold. And then I don't know. I also think of like sand and dirty, but that doesn't always have to be a desert. But yes, dry, hot, windy, changing temperatures a lot. So I looked. It can get up to 38 degrees Celsius in the day and negative 4 degrees Celsius at night in a desert. So really big temperature changes. But what about a coastal area? What if we went to one of the beaches in Honduras? What would it feel like? I think it would be warm. It would have a fair temperature, I would say. What's called humid, where there's a lot of water in the air, and it's almost always the same temperature. So it doesn't get super hot or super cold. Maybe it only changes by like 5 degrees Celsius from night till day. So why is that? Why is there such a big difference between our deserts and our coastal area? And it all has to do with the amount of water. So our deserts are described as places that don't have water, whereas our coastal areas, of course, are surrounded by the ocean. So water's high heat capacity absorbs or takes in all of the heat, all of the energy from the sun, so that the temperature won't change. But places like the desert have no water to do that. They have sand, maybe they have some dirt, they don't have many things that will take in the energy, and so that energy goes into raising the temperature a lot. But once the sun's gone in the middle of the night, the deserts get really cold because they have nothing to trap that heat, nothing to keep that heat or energy in the environment. It just goes away. It goes into the atmosphere, and then they have to wait till the next day when the sun's out, and it changes back and forth a lot because everything in that environment of a desert has such a low heat capacity. But our coastal areas, really being the ocean, has such a high heat capacity that our temperatures stay the same because this water takes a long time to warm up all day, maybe weeks, but it also takes a long time to cool down. So as the water is slowly cooling down, it's slowly letting out some of that energy, some of that heat, and that's why it's almost always the same temperature, is because we're always letting out just a little bit of heat rather than in our desert where it's either a lot or none. So some questions just to think through this. So Mr. Max is trying to build his own comal to cook tortillas, but he's not sure what type of metal to use. So he wants to use a metal with a low heat capacity so it will transfer heat quicker. To find out which metal is best, he puts a piece of iron and a piece of steel next to a fire to see which one will heat up faster. After being next to the fire for the same amount of time, the iron is hotter than the steel. Which metal should Mr. Max use? So I'm also asking which metal has a lower heat capacity. So because one heats up quicker, I want the one that heats up quicker, which has a lower heat capacity. Always think when we have high heat capacity, we're talking about water, and water takes forever to warm up, but we want something that warms up fast. So the one that has a higher temperature will have a lower heat capacity. So this says the iron is hotter than the steel. So if I want it to cook my tortillas better, I want the iron. So the iron has a lower heat capacity because its temperature rose more than the steel. So I should use that one for my tortillas. I have another question. So Mr. Max is trying to cool down on a very hot summer day. So he decides to fill up a small swimming pool, but he wants to use a liquid that would not change in temperature much under the hot sun. He heard that liquid nitrogen has a higher heat capacity than water, so he wants to try to fill his pool with that rather than water. Would this solve his problem? Why or why not? So most people use water in their swimming pools because as a high heat capacity, we can get in, we can cool down very easily. It takes a while for the water to warm up, and it's nice to cool off on a hot summer day. But this liquid nitrogen has a higher heat capacity than water. So in theory, it seems like it would be a good idea. It seems like it would cool me down even faster than my water swimming pool would be. So why might that not be a good idea? Well, let's look at what liquid nitrogen is. So in theory, liquid nitrogen would take more heat to warm up than water. That's great. That's what we want. So it would solve my problem and stay colder longer. However, liquid nitrogen is so cold it will burn your skin. So I should just stick with water. So for us who don't know what liquid nitrogen is, I have a video here that, I have it linked in the Google Classroom as always, but some fun things to notice as we're watching this liquid nitrogen just for fun to see how it works. Maybe teach you guys what liquid nitrogen is, but it looks like clear water, but it's boiling at room temperature. Why is it boiling? Well, that's because nitrogen is normally an air at room temperature, so it's warming up and changing from a liquid to a gas at room temperature, rather than water, which needs to be heated up to change from liquid to gas. So how do the objects change? Well, they start off soft maybe, but just after a few seconds in liquid nitrogen, they freeze and turn to a solid and break very easily. They become brittle. And the last thing I'm going to say about liquid nitrogen is we always need to wear gloves or protection because it will burn you. So if I tried to go swimming in this, my whole body would be burned just like as if I was in a fire. So it would kill my skin and be very, very dangerous. But here's a video that's just kind of fun to learn about liquid nitrogen. But what we all are learning about is heat capacity. So some takeaways is that our heat capacity is how much energy gets put in, how much energy an object can take without changing its temperature. So water takes a lot of energy without changing its temperature, but things that have lower heat capacities are really important too. Like my first question about my metal. Sometimes we want things with low heat capacities because we want things to heat up quickly. Other times we want things with high heat capacities because we don't want them to change temperature. So I hope that kind of gives you guys an idea of what heat capacity is, and we're going to start learning how to use it in calculations now.